First of all, I'd like to thank the organizers for this wonderful opportunity, and also I thank Eugenia for her guidance in the EMCAT program, and also thank all for coming here against the promotion by Chris this morning. And well, today I'd like to tell you how the language of double categories can help us understand relations relative to factorization system. So, as you probably know, double categories have two kinds of arrows, which enables us to deal with functions and relations in a single structure, rather than separately having the category of functions and the bicategories of relations. In this sense, the double categories of sets, functions, and relations is our prototype. So, in this talk, I'm going to explain the construction of double categories from stable factorization systems and provide an overview of the characterization of the image of this construction. Right? So I divided this talk into three parts. First, I'm providing the background of this study, and then I'm moving on to the structure that characterizes the double categories that we have in mind. And then I'm going to explain the main theory of the study, and this talk is based on this reference, which is joint work with K-scale. Okay, so let's get started. So first, let me define the double categories. A double category is an internal to category in the two categories, and its data is given like this. And we take the category D0 as a category of objects in vertical arrows, while we take D1 as a category of horizontal arrows and cells between them. So in our convention, the composition of horizontal arrows are associative just up to isomorphism. Right. And the important examples include the double categories of profunctors or toposes, but our focus is these double categories. The first one is the double categories of relations on a regular category. It has objects as its objects, and arrows in C as vertical arrows, and relations as a horizontal arrows, and the cells are defined using the internal inclusion order in the regular category. And the second one is the double category of spans. Its vertical part is the same, but this time the horizontal arrows are defined as spans. I mean a pair of arrows whose domains are the same. And the cells are defined like this. It is an arrow from vertex to vertex, which is compatible with the two vertical arrows. And what we want to do is unify these two double categories in a suitable way. And for this matter, it is well known that factorization system plays an important role. Suppose you have a category with finite limits and it has a stable orthogonal factorization system on it, and we write it as E and M. Then we can define M relations. An M relation from A to B is an arrow into the product of the two objects, which belongs to the right class M. This is a common generalization of relations and spans. Because if you take the factorization system consisting of the regular morphisms and monomorphisms, then you will have usual relations as M relations. While you take the trivial factorization systems whose right class include all the morphisms, then the M relation becomes spans. Right? And as in the usual relations, we can define the composition of M relations. It's defined like this. It involves pullback in the category C and factorization with respect to that factorization system, right? But the point is, thanks to the stability of this factorization system, meaning that the left class is stable under pullback. We know that this composition is associative and unital up to isomorphism, which leads us to define the double categories of M relations. As we expect, the vertical part is the category C, and horizontal arrows or M relations, and cells are defined the exact same way as what we did in this case of spans. Okay? And so when I write this diagram, what we did is we constructed the double categories of relations from stable factorization systems. And now we can get to specify our two goals. First, we want to know what structures on double categories characterize the double categories of M relations. In other words, we want to delineate the image of this construction in terms of double categories. And second, we want to know how we can recover the factorization system from the resulting double categories. And I'm going to answer these questions in this talk. Right. But the special case are already examined. The double categories of spans and relations were characterized by Aleatory and Lambert, respectively. And our characterization theorem includes these results as special cases. Right. So let's move on to the second section. But before that, I'm going to touch on the notation I'm going to use. When I write a triangle cell like this in a double category, I mean a cell whose top horizontal arrow is the identity. So I usually contract the horizontal identity arrow into a single object. But anyway, let's move on. So the first structures I'm going to explain is restrictions and extensions. Suppose we have triple R, F, and G, then its restriction is defined as a cell that fills this triple with the upward universal property, by which I mean given a cell whose bottom part is R, F, and G, it uniquely factors through this cell row. And the extension is a vertical dual notion of this. And we usually see these notions as properties on cells because, as is always the case, restrictions and extensions are unique up to isomorphisms. So we call a cell Cartesian or off-Cartesian and write it like this. It arises as a restriction or an extension of a given bottom part and the top part. Okay? And the first observation is for a double category D, every triple has restriction if and only if it has an extension. And if these equivalent conditions hold, then double category is called an equivalent. And the important examples include the double categories of profunctors, and also our double category of M relations are also an equivalent. Because given this triple R, F, and G, its restriction is given by the pullback of M relation R through the product of F and G. But the intuition behind this is that restriction is a substitution of two functions into relations. Okay. And the second one is tabulators. A tabulator of horizontal arrow is a universal triangle cell whose bottom arrow is R. This was introduced by Brandis and Perret. And when this cell kappa is off-Cartesian, then we call it strong tabulator. And again, the double categories of M relations has strong tabulators for all the horizontal arrows. The proof is simple, at least conceptually, because an M relation is defined as a special kind of span, so it itself gives the tabulator of this M relation. And the intuition behind this is tabulator is a comprehension of relations. If you are familiar with comprehension scheme in vibrations or just comprehension axiom in set theory. But anyway. And the final structure I'm going to explain is Bechdel fallbacks. But in this case, I'm going to explain this with a simple case. Suppose you have a Pohlbach square in set, then it gives us the equality relation between A and B. The left-hand side is the simultaneous image of P and Q, while the right-hand side is the kernel of F and G. And how can we translate this into double categories? Well, we can translate it as the equality of these two cells. The left-hand side is the identity cell on this vertical arrow from D to C. And this one is the composite of an Cartesian and Cartesian cell. And this is because the left-hand side is given as the extension of P and Q, while the right-hand side is given by restriction of F and G. So this is equivalent to say this equality. And from this observation, we define Bechdel fallback in arbitrarily double category. I mean, a double category has Bechdel fallbacks if it's for a given Pohlbach square in the vertical category of this double category, this presentation holds. Okay. So now we've got everything in order, but before moving on to the main theorem, let me explain the technique we use in proof, which I find very cute. So I'm going to introduce this lemma, which I call sandwich lemma. This is about the diagrammatic reasoning in the double categories. And it says that suppose you have an off-Cartesian cell sandwiched between Cartesian cells, then it becomes Cartesian cell. And the second statement is dual statement. And I'm not going to prove this now, but instead I'd like to demonstrate how we use this. Okay? And for that purpose, I'm going to prove this toy proposition. It states that equivalent with Bechdel fallbacks, the class of horizontal arrows that appears as extension of some span F and G, it is closed under composition. So how can we prove this? Well, suppose you have two Cartesian triangle cells whose bottom arrows are R and S. Then take the fallback of these arrows. Then, by the assumption, we can present the cell in the middle as the composite of Cartesian and Cartesian cell. Then here you have a sandwich. So we know this is an Cartesian cell. Although I didn't mention anything about this, but the composite of two Cartesian cells in a vertical direction is again Cartesian cell because it shows the downward universal property. So we know that we have the triangle cell whose bottom, Cartesian triangle cell whose bottom arrow is the composite of R and S. So this completes the proof and how it works. Okay? Digression aside, let's move on to the main theorem of our study. Okay, so this is a statement, and it says, suppose you have a double category, then the following are equivalent. The first one is the double category is equivalent to the double categories of M relations. The second one is our characterization of M relations. The first statement is that double category is Cartesian equivalent. And by Cartesian, I mean a Cartesian object in the two categories of double categories, but you can naively think of it as double categorical finite product structure. And the second one is that double category has strong tabulators and vector formats. And the third one is the class of vertical arrows, which appears as a tabulator of a horizontal arrow into terminal object. So you can see this F appears as this tabulator. And this class is closed under composition. Okay. And if the second statement holds, then the factorization system can be recovered from this, because we can take the right class as this class of vertical arrow. So we achieved the second goal that I mentioned earlier. Right, so let's move on. And from another perspective, what we did is that we obtained the correspondence between stable factorization systems and double categories with suitable structures. So it is natural to desire some correspondences between properties on stable factorization systems and double categories of M relations. And here's a table of the correspondences. And in the next slide, I'm going to explain some of these correspondences. Okay? First, our double category is called unit pure if given a cell whose horizontal arrows are both the identities, then it must be the identity cell on that vertical arrow. So it must be, the vertical arrow must be the same. This was introduced by Holly, and we figured out that the double category of M relation is unit pure if and only if the left class E is included in the class of epimorphisms. And next, double category is called locally preordered if there is at most one cell for each thread. This was also called flat by some authors, but anyway, the double categories of M relations is locally preordered if the right class M is included in the class of monomorphisms. And finally, a double category is called Cauchy. This was introduced by Paré. If every horizontal adjunction can be presented as a companion conjoint adjunction. And we figured out that double categories of M relation is unit pure and Cauchy if and only if all the monomorphisms belong to the right class M. Okay. And from the last two propositions, we can recover the results by Lambert, because from these two conditions we detect what the right class is, and double category of M relation is unit pure, Cauchy, and locally preordered if the factorization system is given as the regular epimorphisms and monomorphisms, which means the underlying category is regular. Okay, so this is what I wanted to say, and this is our future direction. Well, first I'm going to elaborate on the connection between our study with allegory theory. And also I'm going to give some connection between vibrations and double category or virtual double categories, which is my work in progress. And these two future direction is based on my belief that there is something like double categorical logic. And for that purpose, first I want to create something like internal language of double categories. So that's my future direction. And the references. Anyway, thank you for listening.
Thank you for your nice talk. Questions, remarks?
Could you go back to slide 12, I think it says, where you have the construction. Yeah, so here you've got these two presumably functors going in either direction. Is there an adjunction between them?
To be honest, this is not an adjunction. I think what I mean by this arrow is that there is a just a correspondence of the object-wise. Yeah.
That's the point. Okay.
Yeah.
Further questions?
Thank you for the talk. It's very interesting. Do you know the relation between the next localization induced by the stable factorization system, and in particular perhaps its category of fraction or something like this, with the double category you consider with this relation?
So what resolution?
What is the relation between the double category of the relation for your standard factorization system and the category of fraction of relative to the next localization induced? Because, okay, in one you will have to span with the left map on one side, but should not they be related in some way at some point?
Yeah, that's an interesting question. Yeah, I know that someone do type of thing, but I've never thought of that. So, I mean, the direct connection between that double category to ours. Yeah, I think the same.
I have a small technical question. The E inside of FP and the mono inside of M, what implies the other? Is it because of orthogonality, or it doesn't follow the unit pure Cauchy is stronger than unit pure, right?
Okay.
Maybe correspondence is mono in M, but then it should imply that E is inside of FE, right? Or am I misreading?
Yeah, but
What is it? Arrow.
so we obtained this correspondence by proving what is a horizontal adjunction in a concrete presentation. And to prove this, the assumption of unit pureness is necessary, I think. So I'm not sure what happened. Just think about the Cauchy double categories. But is this answering your question?
I thought it was a very easy indication why the one implies the other. I will ask you.
Further questions?
Sorry, I have a second one. So you have this notion of M relation, but then when you do the quotient of M relation, when you effectivize and look at it should define the notion of epimorphism regular or quotient relative to this, and are this quotient in the left class, the stable left class, or in the closure of it, or?
Could you repeat that again?
Are the quotient of M relation related in some way to the left class of the factorization system? Are they left class, or are they to closure by something?
So you mean by? So sorry, if that's wrong. You want to know what the left
At the very beginning, when you define this notion of M relation as an M subobject of the product, is there a way to have a notion of a corresponding quotient? And what is all this quotient to be related to the notion of the
okay, now I got your question. I think it's not a big deal because we're thinking about pseudo double categories, so it's up to equivalence in the two categories of double categories. I think it doesn't matter.
But for the positions on C, it's any category C with a factorization system, orthogonal, as it's called. Is there any condition on C other than being
Finally completeness.
it's completely general. The last picture, yes. C, you give it C, a category C, with an orthogonal factorization system, and no more conditions, no other conditions.
So on the top, yes.
Yeah, it must be stable as well.
Yes, stable. Yes, but there is no need to have a regularity. No. So, at least. Okay, thank you.
Well, I think further questions you can ask during the rest of the day. We thank